All right, so we're going to pick up talking about chi-square tests. We only talked about one, which was chi-square goodness of fit. And there are 3 different types of chi-square tests. And I think goodness of fit is kind of off by itself because you take a distribution of data and you're trying to match it to some idea you have in your head, whether that be that they're equally likely or they're distributed based on these percentages. Okay? The other 2 tests are a little bit different. The mechanics are similar, but a little bit different. And there's 2 tests, and you're going to need to be able to tell the difference. If you can't tell the difference, you'll name the wrong test on the AP exam, and then you'll write the hypotheses in the wrong way. And then you will only get a 2 instead of a 4 because you picked the wrong test. So let's not do that. So there's 2 tests, and today all we're going to do is talk about the 2 tests. We're not going to actually do a test. We're just going to talk about the difference between the 2 and practice the difference between the 2. So that way, when you get right down to it, you learned originally how to tell the difference. If I taught all of one type today and all of one type tomorrow, you would never have a chance or opportunity to go through and select which test was which and how to do them. So today we're just focusing on which type of test do you use, okay? The first type of test is a chi-square test of homogeneity. In this case, you're talking about if the distributions are the same. Now, some of you are looking at me going, that sounds a lot like a goodness of fit test. It is, in a sense, but instead of matching a distribution to a theory, you're trying to match distributions to each other. So our distribution's the same. That means you have 2 separate distributions from 2 separate populations. And it could be more than 2. So 2 plus distributions from 2 plus populations. For example, if I wanted to know the distribution of grades, A, B, C, D, F, for my statistics classes, based on gender, male and female, I would do a chi-square test of homogeneity if I was interested in the grade distribution from last year compared to the grade distribution of this year. That's 2 completely separate populations I'm pulling data from. So that would be me comparing 2 distributions to see if they are the same. That's chi-square test for homogeneity. A chi-square test for independence is where you're looking to see if variables are independent. That's the question that you're asking. And so that means you have 1 population that you're pulling data from. 1, singular. Not 2 samples, not 2 surveys, 1. Okay, so that's going to make the difference. And then one more note, I know we're not talking about any of the mechanics of the test today, but I do want to go ahead and say the degrees of freedom are a little bit different here. We've had n-1 degrees of freedom for pretty much every single test, except for a 2 sample T where we couldn't figure it out anyway. We had to use an approximation in the calculator. But here, you don't have a number of categories because you might have 2 variables. So that gets tricky. So it's not n-1 anymore. We have rows -1 times columns -1, as in from a table. So generally, your data is going to be presented in a table because of the multiple variables. Okay? So keep that in mind for tomorrow. So all we're going to do today is go through and look at these scenarios and decide which test to do. That's all we're doing. That's all your homework's going to be. Okay? Now, for each of the following situations, state whether you use a chi-square goodness of fit test, a chi-square test of homogeneity, a chi-square test of independence, or some other statistical test. Now, it's trying to trick you, and don't fall into the trap. Remember that chi-square tests are only for categorical data. If they give you some quantitative measure, you don't have a category. So you just have a list of data, so you can't do a chi-square test. Keep that in mind. All right, here we go. Number 1A. A brokerage firm wants to see whether the type of account a customer has affects the type of trades that customer makes. It collects a random sample of trades made for its customers over the past year and performs a test. We need to know how many populations this sample is coming from. and it says a random sample for its customers over the past year. So that is one population. I don't have two different samples pulled from two different times. I just have one sample. Because it's one sample, I'd be doing a chi-square test of independence. Okay, always look at the population. For the next one. That brokerage firm also wants to know if the type of account affects the size of the account in dollars. It performs a test to see if the mean size of the account is the same for the three account types. It's easy to get suckered in, but it says that one of your variables is the size of the account in dollars. And that is quantitative, and you can't do a chi-square test with quantitative data, so this is some other statistical test. Last one on this page. The Academic Research Office at a large community college wants to see whether the distribution of courses chosen is different for its residential and non-residential students. It assembles last semester's data and performs a test. Well, we have two separate populations. You have the residential population and the non-residential population. So this would be a chi-square test of homogeneity. We're looking to see if residential and non-residential have the same distribution of courses. Okay? All right, hope we're seeing how this works now. All right, this is number 2 from your book. I don't know why that got cut off. We'll put some more scenarios. Is the quality of a car affected by what day it was built? A car manufacturer examines a random sample of the warranty claims filed over the past 2 years to test whether defects are randomly distributed across the days of the work week. Well, what kind of chi-square test is it? We're trying to see if it's randomly distributed over the days of the work week. So this is chi-square goodness of fit. Where do you think it should be equally likely no matter what the day? Okay? All right, next one. A medical researcher wants to know if blood cholesterol level is related to heart disease. She examines a database of 10,000 patients, testing whether the cholesterol level in milligrams is related to whether or not a person has heart disease. Cholesterol level in milligrams can't have a quantitative value, must be other. A student wants to find out whether political leaning, liberal, moderate, or conservative, is related to choice of major. He surveys 500 randomly chosen students and performs a test. How many populations do you have? 1. So because it's 1, we're looking at a chi-square test of independence. Okay? Look at your populations. All right, I've got a few more examples here. We're just looking at the type of test. A random survey of autos parked in the student lot and the staff lot at a large university classified the brands by country of origin, as seen in the table. Are there differences in the national origins of cars driven by students and staff? Well, we have a random survey parked in the student lot and the staff lot. That makes 2 populations, so that makes this a chi-square test of homogeneity. Got 2 separate samples, 2 different lots. Last one. Medical researchers followed 6,272 Swedish men for 30 years to see if there was any association between the amount of fish in their diet and prostate cancer. Well, how many populations do you have? You have 6,272 people that they followed. And they're looking for an association. So this is a chi-square test of independence. So today, all I'm going to give you for the assignment is a list of problems that you are not going to do because we have yet to do the mechanics or anything for a test. And you're going to go through and name which test you are going to do. All right? This will hopefully help you get better at it because since the mechanics are identical, it really comes down to can you name the test and give the hypotheses that are correct.